Hey chemistry students, this is Mr. Resentas, and today I'm going to talk about ionic bonds and nomenclature, or how we name these compounds. I'm in chapter 7, page 225. Follow along. You'll definitely need your periodic table, your periodic table that has the oxidation numbers in the corner is most helpful. I realize that you might not be able to see what I mean by oxidation numbers, but I gave you one of these periodic tables, and you'll need it for reference whenever we try to determine the ionic bonds. Right. If we get started, first we use electronegativity differences to classify the different types of bonds. If the electronegativity difference is between 1.7 and 3.0, then it's an ionic bond. So anything less than 1.7 is really a covalent bond. There's a couple different types of covalent bonds. We're going to talk about what a polar bond is a little bit later. But the point is that ionic bonds have a large electrical attraction to one another. That's the point. And we already discussed the trend that we find that when we move from left to right across the periodic table, the electronegativity increases, and fluorine has the greatest electronegativity. So we would expect those elements in group 1 and group 17 to have a large electronegativity difference, and that is the case. Now, if you want to find the electronegativity, there are tables that give that to you, and those tables are in your book. The only point I want to try and make, it here, is that you can find the value for sulfur and hydrogen, determine the difference, and then determine the type of bond. And so, because the difference is rather low, also because you don't have a metal and a non-metal, this is not an ionic bond but a covalent bond. So that would be for our first one. Second one, between sulfur and cesium. Well, as you can see, there's a greater difference between these two, higher than 1.7. So this is going to be an ionic bond. All right. The next one, between chlorine and sulfur. If you look on your periodic table, if you look we have chlorine and sulfur here for these two. And as you would expect, we don't have a metal and a non-metal. That's a covalent bond. Alright, so now what if we look at between chlorine and calcium? Well, if we look, chlorine on our periodic table is here, and calcium is here. Well, now we do have a metal and a non-metal. We just typically don't describe them in that way because we're describing the anion before the cation. We're describing the non-metal before the metal. So this is definitely an ionic bond. Don't let that fool you. All right. And also, you know it's an ionic bond because the differences are great. So if I gave you these values, and I gave you these differences, and I gave you this grid, you should be able to determine the type of bond. What about between chlorine and oxygen? Chlorine and oxygen. Well, we don't have a metal and non-metal. I wouldn't expect it to be very much. It isn't, and so it's a covalent. All right. The covalent bonds are ones where electrons are shared. It's not bound by electronegativity. What about chlorine and bromine? Let's have a look. Chlorine and bromine, and bromine is here on the right next to chlorine on the periodic table. They're in the same group, so no, you would not expect it to be in a covalent bond, an ionic bond. All right. So ionic bonds have a large electrical attraction. Covalent bonds are when electrons are shared. All right. Now, ionic bonding forms from opposite charged ions, and that's basically what I was showing you. And when this happens, we have something called a compound. Compounds are different from molecules, and I want to make the distinction. Compounds are crystalline. They're crystalline. They mostly dissolve in water, whereas molecules don't. You see, a molecule, you should be able to get to a neutral element. You should be able to get to a neutral group of atoms whenever you have a molecule. Whereas compounds, you don't find that. Really, with compounds, they're able to separate in water, and you'll find that molecules don't do that. Compounds are different elements, whereas molecules can be the same elements added together, like in the case of the diatomic molecules. The formula units show the ratio of elements. All right, so if we want to give the formula for a compound, let's start with calcium, which has two electrons in its valence, and so this is the Lewis dot, plus fluorine, which has 7 in its valence, and that's the Lewis dot. And because this has 2 to give up, we want electrically neutral, there will be 2. So we'll end up with calcium. That's going to have 2 plus, and then you're going to end up with a fluorine, which has all of its electrons, all 8. So it's a happy octet, and another one with 8. It too is a happy octet. So the formula here would be CaF2, calcium fluorine. Now, you always write the metal first. Okay? And the charges must be balanced. All right, to achieve electrical neutrality. So we're always trying to, and that's why I had to add 2 fluorines in order to have a balanced charge for electrical neutrality. Polyatomic ions are this is a group of covalently bonded atoms that have a charge. So the polyatomic ions are covalently bonded and charged with either positive or negative. For example, if we use copper 2 plus the nitrate ion, and if you want to know the nitrate ion, you've been given a table with the polyatomic ions on it, but you also have a table that lists the polyatomic ions on page 232, and that's where you'll find this nitrate ion, and I could do a Lewis dot, but I don't have I'm running out of time. Now, because I use copper 2, because the nitrate only has one negative. Copper can come in either 1 or 2 if you look it up. And the reason why I want to use 2 is because it needs to in order to become electrically neutral. So it'll be CuNO3, and I'll need 2 of them. So you only use the parentheses whenever you're adding more than 1. So this would be, the way we would name this is copper 2 nitrate, and the nitrate ion is named for you. So that shouldn't be a problem. We could do the same with aluminum, and if I look aluminum up, aluminum has an oxidation number of +3. It looks like I'm going, and then if we use the nitrate ion again, I'm going to need how many of them? Well, I'm going to need 3 of them. And this is referred to as the crisscross method, because the aluminum oxidation number becomes the subscript for the nitrate ion. And so this is AlNO3, and I'll need 3 of them. And that 3 came from this because I need 3 of them in order to make it electrically neutral. All right? And so that would be aluminum nitrate. All right. So let's try naming a few, and let's try naming a few more. Just if I name and then the formula. If I had AlF3, that would be aluminum fluoride. And if I had magnesium oxide, well, magnesium, I looked it up, has +2 and oxygen has -2, so that's just going to be MgO. We want the lowest. We want to reduce to the lowest number. Strontium bromide. Strontium I looked up, +2. Bromide is -1, so it's strontium, and then we're going to need 2 of those in order to balance that out. All right, and then calcium sulfate. The sulfate ion you look up, that's a polyatomic ion. You just look it up in your table on page 232, or the one that I gave you. It's just copper and then sulfate. There's the copper, and you know parentheses necessary because there's only one. You'll find that calcium's oxidation number is 2, and the sulfate is -2, and that's why you only need 1 of them. All right.